This is one of the most difficult things we do in AP chemistry, the titration between a weak acid and a strong base. I worked this problem out in class. I'm going to work it out again. We're going to consider the titration of 0.1 molar sodium hydroxide, that'll be in our burette, into 0.1 molar hydroazoic acid, that'll be here. The indicator changes color when 10 milliliters of the sodium hydroxide have been added. So that tells us right away that the end point is when the indicator changes color. The first thing we need to do is to make a balanced chemical reaction. We recognize that the weak acid will react with the strong base. However, what we can do is recognize that strong bases, you don't really need the sodium ion. So for net ionic, we keep the acid together, but we think of the strong base as hydroxide. It will form a double replacement reaction. H with OH makes water and sodium azide. But again, we'll cancel out the sodium because the sodium is just a spectator ion. This is a reaction about the azide ion, where sodium, frankly, just doesn't matter. For the equilibrium, we would imagine that HN3 as an acid is going to be a hydrogen donor. So hydrogen plus the azide ion. Its Ka value, you can look it up in your book, is 1.9 times 10 to the minus 5. For the conjugate base form of this, the azide ion, we can conclude that as a base it is going to be a hydrogen acceptor. So there it is, accepting a hydrogen, becoming neutral. And it accepts it from water, so when we take it away from water we're left with OH. The Kb is actually going to be the Kw over the Ka, and when you do the math it turns out to be 5.3 times 10 to the minus 10. Let's add 8 milliliters of sodium hydroxide to the 10 milliliters of the hydroazoic acid. That won't quite take us to the end point, but it'll be close. So we have 10 milliliters here, and we'll add 8 milliliters here. This reaction needs to occur in 2 steps. In the first step, we're going to have this stoichiometry that happens. The weak acid will be reacted by the base. So I'm going to rewrite that expression. The weak acid reacts with the base to give us the conjugate and the water. And when this happens, I'm going to look at the number of moles for the stoichiometry, the initial, the change, and the final number of moles. So in doing so, I remember that molarity is moles over liters. So to find out the number of moles, I'll just say that moles equals molarity times liters. For the weak acid, the molarity was 0.1, and the liters were 10 mils, so 0.010 liters. For the weak acid, that tells me I'm 0.00100, following sig fig rules. Doing the same thing for the base, it's 0.1 molar base, but I only have 8 mils, making it 0.008. The math tells me it's 0.00080. And we can assume that we'd have 0, and who cares about the water? Water won't really make a difference in this case. In stoichiometry, we have a limiting reaction question. The smaller one will become 0. The smaller one gets used up, and there'll be some left of the other. I lose the entire amount, 0.00080, and I lose that same amount here because the stoichiometry is 1-to-1. But at the same time, I gain that much as a product, 0.00080. And so, finishing the math, this tells me 0.00020 moles, 0.00080 moles. Now, the solution was a reaction of 10 mils of acid plus 8 mils of base. So my total volume now is 18 milliliters. I have to remember that this is moles, but I need to put it into molarity. So I've got to divide it by those 18 milliliters as liters. And in both cases, when I do the math, I find out that my final molarity of the acid is 0.011 molar. my final molarity of the conjugate base is 0.044 molar. But that's only part one of the question. Now what we've got to do is the stoichiometry, or is the equilibrium. Since we have a weak acid left, along with this weak acid's conjugate base, there's going to be equilibrium that happens. So next we go and we say the equilibrium expression, HN3, gives us H plus 1 and N3 minus 1. I'm going to use ice now. The difference with ice is E stands for equilibrium, and it's all measured with molarities. So right away, this value becomes my initial molarity of the acid, this value my initial molarity of the salt, and we'll assume that there's no hydrogen in the solution until equilibrium is reached, in which case a little bit will form, X will form. Hopefully X is a small number, because that lets us make this assumption and this assumption. The Ka value we need is 1.9 times 10 to the minus 5. That Ka value represents products over reactants. There's my two products multiplied over the reactants. Luckily, the stoichiometry is 1 to 1 and 1 to 1. That makes this all much easier. By the time I solve for this, I recognize that it's equal to 0.9 times 10 to the minus 5. And X is equal to, let me grab my calculator, (4.8 times 10 to the 6, got to count, minus 6. That represents the hydrogen ion molarity, and so by taking the log of that, I can see that my pH is 5.32. There's a lot involved here. You have to do a lot of stuff in order to get this to work. But this is the question that I worked on the board. Now you might notice that I never ended up using this expression, and I won't use this expression as long as I have combinations of acid and conjugate left over. But if I no longer had acid, if I only had conjugate left over, and that's exactly what I would have at the end point, then this is the expression I'd use with this K value. So at the end point I'll use this. But that's for a different day.